Estimation and image reconstruction for dynamic X-ray tomography.
Great, thank you very much. So the project I'm going to talk about is a joint work with Martin Burger and with Andreas Hauptmann from UCL, oh I forgot, Henrik Dirks, who now actually left to industry, and also with Tapio Helin and Samuli Siltanen from University of Helsinki. Okay, what we want to do is we actually want to reconstruct continuously moving objects, like in this example right here. And this would be a rather simple task if we would consider a full angle measurement for every single time step. But this is actually not what we want to do. So in this case, we really want to only take as few measurements as possible in every time step, which means that in the ideal case, we only expect to have a single measurement from one angle per time step. Anyway, we not only want to obtain a single image from a motion-corrected image for a specific time step, but instead we want to obtain the whole sequence of images, so one image for every time step. Okay, in order to do that, I will start by talking a little bit about dynamic reconstruction in general, and there I will also introduce a time-dependent variant of the Radon transform, and incorporate this into a variational model for reconstruction. Since the model I want to use in the end also includes a term for estimating motion, I will then make in the second section a short excursion about the topic of estimating motion, and then for the third part I will go back to the main topic, which is the dynamic reconstruction, and there will very shortly comment on the minimization of this model. I will show some measurement setups that we want to use, and of course in the end I will show some results. Okay, so let's start with the reconstruction part. So always when we are working with X-ray tomography data, we are having to deal with the Radon transform. So in the static case, the Radon transform is defined like this. And this Radon transform basically consists of a line integral of the attenuation coefficient, which is here denoted by u. And we can think of it like a projection of this functional u onto a vertical line. And this projection results in the so-called sinogram, which is here denoted by m, and the sinogram is dependent on the measurement angle theta and the distance to the origin, which is here called s. And the sinogram evolves like this. So if we have a static data set like these three stones right here, we start measuring from, in this case, we start measuring from the top, and then we rotate a little bit, make the next measurement, and with all the projections we get, we obtain this sinogram here on the right hand side. So this sinogram consists of, in this case, 30 different angles. And if we want to reconstruct this static data set out of the sinogram right here, we have to solve the inverse problem RU is equal to M, where R is the static Radon transform. However, as I said, I do not want to work with static data, but instead with moving objects. And if during the measurements the objects start to move, of course the sinogram does look a little bit different. So here, when we start the measurements, the stones are placed in the center of the image, which means that this here only depicts the situation at time step 1, and then with every time steps the stones move a little bit further apart, and therefore the sinogram here is also dependent on the time. Okay, since this is a little bit different, we also have to adapt the definition of the Radon transform a little bit. And therefore we assume to have a fixed and bounded time interval, which is here 0t. Since the objects are moving in between the time steps, it's of special importance to notice that also the measured angles do change between the time steps. So therefore we need to define the set of active measurement parameters, which is denoted by I, and the set basically contains those angles that are active at every single time step. And with this definition, we can introduce the time-dependent variant of the Radon transform, which is given in this box here. And as you can see, the time-dependent Radon transform basically consists of parts of the static Radon transform, which are only applied to those angles that are actually active in this specific time step. Okay, when we do that, we get an operator which is still well-defined, bounded, and linear, which directly follows from the characteristics of the static Radon transform. And yeah, with this time-dependent gradient transform, we want to solve the inverse problem AU is equal to M, where, as I told before, the sign of M is now also dependent on time. So due to radon, we know that there exists a unique solution if we know about the radon transform for every angle theta, every s, for every time step t. However, this is certainly not the case in our approach because we only want to use in the ideal case only a single theta and s for every time step, which means that there is of course no uniqueness guaranteed for the approach that we use. And in order to overcome this problem, we want to solve this this minimization problem in a variational approach, and this looks like this here. So in the beginning we have the data fidelity. And for this data fidelity, we consider the L1 norm and the squared L2 norm. So usually the L2 norm is the more standard choice for reconstructing X-ray tomography data, but since we are dealing with really highly undersampled data, we need the norm which is really robust, which is why we also want to try the L1 norm for this approach. And then of course we have a regularizer. For example, we can use the total variation regularization. Okay, we still have a problem because the lack of information in every single time step is just too big. So usually when we want to reconstruct static data sets, we need information from about 15 angles or something like that in order to get a proper image in the end. So if we now only take a single angle per time step, we cannot reconstruct the time steps independent from each other. So the idea that we have is that you also want to include the information of all of the other time steps to reconstruct a single time step. And we want to do that by estimating motion fields in between the time steps. And the intention behind is that if we have some information about the object at time step t, and we know how the object evolves between time step t and the next time step, then this also gives us some information about the situation at time step t plus 1. Okay, so in the end, we want to obtain t plus 1 reconstructed images and t motion fields between those images that serve to connect the information. Okay, that means that we also have to adapt the variational model a little bit. So the first terms here are just the variational model we saw before. So this is the data fidelity for reconstruction and also the variation for reconstruction. But since we also want to estimate the motion field, we need a second data fidelity, which is this one here, which is the term for estimating the motion. And the motion is here denoted by v, the velocity field. And since this is the second variable in this model, we also need a second regularization, which is RV right here. As you can see, this model gets minimized with respect to u and to v, which means that as a solution for this model, we get the image intensities of the reconstructed images and the velocity fields for all time steps. Okay, now the question is, of course, how does this data fidelity for estimating motion looks like? And therefore, I will now shortly talk about this topic of estimating motion. And the most popular approach in this field is the optical flow approach, and optical flow is based on the assumption that the intensity of an image is constant along the velocity field v. And this assumption can be written with this equation right here. So we have two consecutive time steps, u0 and u1, and if we start with the image or with the intensity u in pixel x and then just follow the velocity field, then we end up with the same brightness in the next time step. Okay, problem with this is that we only have this one single equation to solve for all components of V. So even if we are only working in 2 dimensions, then V of course also has 2 dimensions, which means that this is again an underdetermined problem, which is why we also want to solve this in a variational approach. And the variational model for estimating motion looks like this. So here we have this nonlinear optical flow constraint, where the most popular choices are again the 1 norm and the squared L2 norm, where here the squared L2 norm is closer to the original idea of Horn and Schunk, but however, the 1 norm just turned out to be more robust with respect to outliers. And then also, of course, we have another regularizer, which can again be TB or also something else. Okay, now the question is, how can we solve this nonlinear optical flow constraint? So, yeah, the easiest idea is to simply fully linearize the whole constraint with the help of a Taylor expansion. When we do this, we get the upper equation right here, which includes the higher order terms. If we now simply ignore the higher order terms, we get this fully linearized optical flow constraint right here. However, the problem with this is that these higher order terms also contain higher orders of the velocity field, the velocity v, and yeah, as soon as the velocity is large, so larger than 1 pixel in this case per time step, then of course also the higher order terms get larger and larger, which means that this linearization is simply only true in case for really very small movements. Yeah, especially if we're working with real data sets, we can usually not restrict the movement that much that this linearized optical flow constraint works for us. This is why yeah, we want to use an alternative method, and in this case we want to use an iterative linearization for, yeah, which we incorporate in a multi-scale approach, and luckily for the case of the L2 norm, there already exists the well-known Gauss-Newton method, which looks like this. And yeah, the Gauss-Newton method is known to converge towards the nonlinear optical flow constraint with the L2 norm. The Gauss-Newton method can basically be derived by linearization around the distance between the optimal solution V and the actual iterate Vn. Yeah, and by now incorporating this, this functional into a multi-scale approach, we can ensure that this distance between V and Vn is always smaller than the actual grid size. Now, of course, the question is whether there's an analog approach also possible for the one norm, and yeah, the answer is yes. We found that this functional here converges, or weakly converges towards the nonlinear optical flow constraint with the one norm. However, if we compare this functional here with the one here in the Gauss-Newton method, we see that we need an additional term, yeah, which we actually need to ensure the existence of solutions for this model. Okay, now we want to see why we actually have to do all of this effort. So I want to compare the fully linearized optical flow constraint with the partially linearized optical flow constraint, and therefore use the Wobberwell dataset. So here at the top left, you see the true ground truth images, and at the bottom, the ground truth velocity field. And then in the upper row, there are results with the L1 and the L2 norm for the linearized optical flow constraint, and at the bottom for the nonlinear optical flow constraint. And as you can see, there are some vertical artifacts, especially here in the purple and also in the blue area for both of the linearized optical flow constraint, and these artifacts are drastically reduced or even vanished completely with the nonlinear optical flow constraint. Yes, as I said before, this large-scale movement is a big problem, especially in real data sets, which is why I also want to show you a real data set. And what you see here is a leukocyte. This is a microscopy data set, and this leukocyte is moving inside of a blood vessel. And yeah, it obviously does move a lot, so it moves like 10 pixels or so in between the two time steps. But still, if we apply the nonlinear optical flow constraint to this data set, we get this result right here, which does not have any strange artifacts or so, but gives us a very nice field. Okay, that's it for the motion part for now, and now we want to go back to the main topic. So, as a short reminder, we already saw two different variational models, so the one for the reconstruction and the one for estimating the motion. And now we basically need to fill in those two models into the general model that we have here. And when we do that, we get, in the time discrete variant, a model which looks like this. So here, in the beginning, we have the data fidelity for reconstruction with the time-dependent gradient transform and the time-dependent sinogram. Then we have the regularizer for the image intensity and the regularizer for the velocity field. And the last one here is the second data fidelity for estimating the motion. So for this model, for the motion estimation part, we only focus on the L1 norm for this data fidelity, since, as I said, it's just more robust. But for the data fidelity for reconstruction, we consider the L1 and the L2 norm. Yeah, for both regularizers, we only use the isotropic total variation regularization, since it's just the most fitting regularizer for the kind of data I will show later on. Okay, one problem with this model is that due to the minimization with respect to u and to v, this model is nonlinear and non-convex. So in order to overcome this, these characteristics make it a little bit hard to minimize. And in order to overcome this, we simply split this model up into two different subproblems. And those two subproblems consist of independent minimization with respect to u and to v. So in the first subproblem, we only have those terms that are actually dependent on u, which is the reconstruction term, the regularizer for reconstruction, but also the term for estimated motion, which also contains the u. And the second subproblem contains all of the terms that are dependent on v, which is, again, the term for estimated motion, and then also the regularizer for the velocity field. So then, luckily, both of these subproblems are again convex and linear, which is why we can simply use state-of-the-art methods to minimize the two subproblems independently. And we do that in an alternating approach, which means that we start by minimizing this one, and then this one again, and so on. Okay, the last thing we need to talk or think about is how do we actually want to measure the data. So the most intuitive way of measuring the data is the one I was more or less already talking about, which is just start measuring at a specific position, then rotate a little bit and make the next measurement and continue like this. However, we thought whether it would make sense to also use other measurement setups. And the second idea that we have is to maybe install a second pair of source and detector for the X-rays in order to being able to measure two, or in this case, we call it multiple angles for every time step. So for this sinogram here, replace the source and detector pairs in a 90 angle degrees, so we use 2 in this case, which means that always 2 sections here of the sinogram depict one single time step. We also had other ideas. So the third idea that we have is something that we call tracking. And for the tracking approach, we start with a static scene, which is where we can make a full angle measurement. Then for the time steps 1 until t-1, we expect to have a dynamic scenery. And in this case, we only make a single measurement per time step. And in the end, we make a full angle measurement again. This might sound a little bit strange, but actually it has some applications one might think of. One application might, for example, be some angiography, where we inject a tracer into a blood vessel. So before injecting the tracer, the scene that we have is more or less static, which is where we can here make the full angle measurement. Then in that moment where we start injecting the tracer into the vein and it's floating through, everything is moving a little bit, which is this part where we only make a single measurement per time step. And then in the end, when the tracer is all around, the scenery is more or less static again, and we can make a full angle measurement. Okay, last but not least, we thought whether it would make sense to not really measure neighboring angles for subsequent time step, but instead, for every time step, just pick a random angle and measure from that direction. Then the sinogram does look a little bit weird, but this is just what we get when we measure from random angles. Okay, now of course we also want to see some results. So the first data set I want to show you is a synthetic data set that we implemented in order to also get some error measures in the end. And as you can see in this case, there's just a white ball which is moving inside of a medium valued ellipse from the left side of the image to the right side of the image. And this image here on the right side is the ground truth velocity field. So you see there's just a red ball, and red in this case simply means a movement to the right side of the image. And for this data set, we expected, or we considered 30 consecutive time steps. And if we now apply the joint model that I introduced before to this data set, we get results that look like this. So these are results for the one data fidelity, and then we have from left to right the intuitive approach with only one measured angle per time step. Then the second one is two measured angle per time step, and the tracking approach with the full angle measurement at the beginning and at the end. And this one is the randomized angle approach. So as you can see, when we start again from the left, the first result, the intuitive one, does look really bad in fact, and the reason for that is that if we make a measurement, in this case we start measuring this image from the top, we have a pretty good estimation about the horizontal position of the ball, but we have no clue at this point about the vertical position of the ball. And the only time when we really have a proper information about the vertical direction is when we shift the measurements about 90 degrees. And in this case, we means that already 15 time steps have passed if we are in this measuring position. And this time is just too big to have a large influence on the reconstruction for the first and also the last time step. So the next one, with pure measured angles per time step, in this reconstruction you can see that we actually do have more or less nice information about the position of the ball in horizontal and vertical direction because of this 90 angle degree between the measurements. But however, there are really strong artifacts in the direction of the measurements, which does also not really need to realize results. For the third approach, a little bit as one might expect before, the first and the last time step are reconstructed really nice. However, in between there's the result is comparable to the intuitive approach, so the influence is still not large enough that is coming from the first and the last time step. But then here for the last image, this is the randomized angle approach, this result does actually look quite nice in my opinion, and the reason for that is basically the same explanation that I already gave for the first one, where we had a huge lack of information in every time step. But in this case, when using randomized angle approach, this is just the most efficient way to get as much information as possible about the horizontal and the vertical and all the other directions that we have. In the most efficient way, I would say. Okay, now we also want to look at some results reconstructed with the L2 data fidelity. This is the same order here: intuitive approach, two angles, the tracking approach, and the randomized angle approach. And one thing one could see is that these results do actually look a little bit different, but the order of quality is basically the same. So again, the first one looks really bad, this one is a little bit better, the tracking approach is really a little bit worse, but the randomized angle approach does look quite nice. So in order to compare both of the data fidelities, I just put them on top of each other. So in the upper run here we have the results for the one data fidelity, and here again the results for the L2 data fidelity. And if we now a bit more slow go through these images, we can try to compare both results. And one thing that is more or less obvious is that the ball is actually a little bit better reconstructed for the L2 data fidelity, so it's at least more roundish. So in the one data fidelity, some balls here, especially for the randomized angle approach, look really edgy, but for the L2 data fidelity it looks a little bit better. But another thing one can observe here is that the ellipse in the background, so the medium valued thing here, is much more static for the L1 data fidelity and also much sharper than for the L2 data fidelity. So this one is really way better reconstructed than here. Okay, this is also the reason why in the end, when we calculate some error measures, so we calculate the L1, the L2 error and the structural similarity index, the results for the L1 norm are a little bit better, at least if we compare the structural similarity index, which is the most neutral measure in order to compare two different data fidelities. However, overall, we can see that the randomized angle approach works the best for all error measurements. Okay, we talked about motion before, so this is also the reason why I, of course, want to show you some motion fields. So on the left side, Okay, I should mention that this is the motion field for the randomized angle approach. So on the left side, this is the motion field for the 1 data fidelity, and the right side for the 2 data fidelity. And yeah, both of these motion fields do look quite different, and to be honest, they don't look really perfect. The reason for that is that we only optimize the parameters for this model with respect to the quality of the reconstruction. So one could, of course, enhance the weight for the motion estimation part of this model, which would definitely give better flow fields in the end. However, this will also make the quality of the reconstruction much worse, which is why we just stick to this not that perfect velocity fields right here. Okay, another thing we were thinking about, or we were not actually thinking about, but we received a comment in the beginning of the week about the robustness of our model with respect to varying intensities. So actually the optical flow approach that we used is based on the assumption of brightness constancy, which means that we do not really expect to have a varying intensity in the images. However, since we are minimizing this in a variational approach, we thought that it could actually work that the intensity is allowed to change a little bit, and so we just tried it out. I hope it's possible to see in the projector here. So we made a new ground truth image for the moving ball, and in this case the ball has a medium intensity in the beginning, then the intensity is enhanced a little bit, then it's increased like a sinus curve, and then in the end it starts to increase a little bit. And then we have, for the randomized angle approach again, the result for the 1 data fidelity and for the 2 data fidelity. So if we first have a look at the result for the 2 data fidelity for reconstruction, we see that it works okay in the beginning, but in this point the reconstruction gets really bad. So this is exactly the point where the intensity of the ball is the closest to the intensity in the background. So here this model does actually have some problems. However, in the 2 data fidelity, these results are still okay in my opinion. So even, let's wait for this time step here, one can still at least estimate the ball in this reconstruction. Of course, a kind of bad thing about it is the estimated motion. So of course the ground truth motion field is still the same as for the first, or for the original idea of this data set, but the estimated motion makes some strange things. So as I said, the optical flow constraint is not really fulfilled here. However, in some time steps this still works, but in most of the time steps this one is really bad, at least for the 1 data fidelity. However, it's nice to see that we still get reasonable reconstructions, at least for this approach. Okay, now I also want to show you real measured data set. And this data set was measured by Andreas at the University of Helsinki, and he simply placed 3 stones in the middle of a CT scanner, and then put the stones apart with every time step. For measuring these time steps, actually we measured every time step from 60 different angles, and the reason for that is that we wanted to use one and the same data set for all of the different measurement setups that we use. So in order to get the right sinograms, we simply chose those measurements from the whole set that we measured and put them together. Okay, so let's have a look at the results. For this data set, we only considered the L1 data fidelity for reconstruction because we already saw that it works a little bit better for the other approach. And then again, we have the intuitive approach, 2 measured angles per time step, the tracking approach, and the randomized approach. And again, we see that the first and the third one do look kind of bad. But however, in this case, the result for 2 measured angles per time step look pretty nice in my opinion. So at least for the later time step. So to be honest, in the beginning we have some strange artifact which might appear like a 4th ball or something. But at least for the later time step, the results are pretty nice. And again, we have the randomized angle approach in the end, which gives again the best results for all of the time steps. So actually we like this result for the randomized angle approach so much that we yeah, we even thought about reducing the amount of angles. So of course it's always better to make less measurements, because yeah, we don't really have such a big X-ray dose, and of course it saves costs and time if we do not make too much, need to make that much measurement. And this is why we tried to reduce the amount of measurements in this approach. So here on the left side we have the result when we only measure 15 angles, and on the right side we have the results where we can only measure 8 angles. So for the 15 angles we still get a reasonable result, so we still can expect where the ball or the stones are situated in every time step, but however 8 angles is still a bit too, yeah, it's just not enough to reconstruct the image properly. However, I already told you before that one needs something about 15 angles also to reconstruct a static image, and in this case we used 15 angles and get 15 images for 15 time steps out of it, which is pretty nice in my opinion. Okay, yeah, that's it for so far. Now I want to summarize shortly what I told you. So I started with the part on reconstruction, where I also introduced the time-dependent gradient transform. Then we made an excursion about the topic of motion estimation, where we saw that a nonlinear optical flow constraint works pretty nicely, and this optical flow constraint was introduced in order to connect the different time steps of the reconstruction with each other. So when merging now both of these tasks, we obtained a joint model for motion estimation and reconstruction, and here with this joint model we tested different measurement setups, and in the end we saw that the best results were achieved for the randomized angle approach. Of course there's still something to do with this project, and first of all we definitely need to test some more complex data sets. So everything we reconstructed right now was really easy to reconstruct, so we only had constant objects that are moving in a more or less simple way, and yeah, we still have to see whether this model still works with more complex data sets. And also we want to consider different motion models, for example something like mass preservation or so, and see whether yeah, the motion estimation part of this model can be yeah, enhanced a little bit. And another thing is that we want to make some analysis of the random angle approach, which means we want to see whether there's a specific distribution of angles or something which works, yeah, which just works the best. So of course the randomized angles might also end up with angles like 1, 2, 3 degree next to each other, which will probably not work out so nice, and this is, well, what we want to analyze a little bit. And then in the end, of course, it would be nice to also extend this model to a fully three-dimensional setting. And yeah, with that I want to thank you for your attention, and I'm happy to answer questions. Questions?
When you look at different fidelity terms, data fidelity terms, they're supposed to reflect the noise statistics of the data.
Yeah, right.
So did you draw from different noise distributions?
No, actually we just used Gaussian noise. We just wanted to try what.
So that's why it's probably the L2 fidelity looked better in this anyway.
In which result do you
some of
mean
the early
it's better?
simulations you have
This one, you mean?
for example.
Oh, you mean that the ball is reconstructed better here? Yeah, probably that's the reason for that. Yeah, one might think about using different noise models here, but actually Gaussian noise is the noise that obviously appears in X-ray tomography, but still the ellipse is better reconstructed with the one on here. So. Yeah, we didn't try actually what happens if we have other noise or multiple kinds of noise.
The noise in the X-ray CT should be Poisson noise of the exponential of the radon transfer.
Yeah.
So it would be not stationary.
That is true. Yeah, we didn't really try that out.
Can you say a bit more about how you solve the joint model? You have n or any time steps. Yeah.
You mean how we? Yeah. Okay. So
Yeah,
this
it's
is. So we solve both of these terms, or both of these subproblems for the entire set of.
Not
of time
sequential,
steps.
so a coupled way. Yeah.
No, we only couple two subsequent time steps. So we first, so we solve this problem for time steps 1 and 2, and then we compare time steps 2 and 3, yeah, and so on. But yeah, we compare all of the time steps first to minimize the model with respect to u, and then we do the same for the second subproblem, and yeah, and so on. But we only compare always two subsequent time steps with each other.
Emma.
Very nice talk. Can you tell me something about how you determine the scale space?
Oh, you determine.
How you determine the scale space? You said for the gradient part of the motion estimation.
Oh, you mean the multiscale approach?
Yeah.
Well, yeah, it's basically the more standard warping approach. So we start with a very coarse grid, and there the model is. So we start in a very coarse grid, and yeah, calculate this iterate right here, and then we warp the result onto a finer grid and calculate the new results. So yeah, it's basically the standard warping multiscale approach that is used.
You mean coarse grid in spatial resolution?
Yes.
So your coarse grid already quite coarse, it's 42 by 42.
Oh no, yeah, yeah, true. But when I talked about this here, this is about the only the optical flow approach, and the images that I showed you for no, they are later than this. So these images are definitely larger. So here, this is a really coarse grid. I think for the results for the joint model, because the images are so small, we use something only like, I don't know, 3 different grid sizes or something. I don't really remember exactly, but still we use the coarse to find a pyramid approach.
Can I ask you something? Because what I didn't don't quite understand is, so the best reconstruction results don't necessarily correspond that the motion is estimated optimally.
Yes.
But you would think, I mean, the whole point is that the motion helps you to better reconstruct, right?
Yes.
But then you're informing the reconstruct, so it's actually better to inform the reconstruction with a worse motion than with a correct motion.
Yeah, well, the reason is just the choice of the parameters here. So of course it would be best to have yeah, a perfect velocity field for the reconstruction, but in order to get that, we have to make another balance of parameters there. So if the balance or the weight of the motion field is just too big, then we don't really minimize the reconstruction part of the model so strongly. So this is
You could turn the optical flow constraint into a hard constraint.
yes, that would be possible.
Any more questions? Okay, if not, let's thank Lena again.
Thank you.